So today we are driving to the fifth class. We have 8 lectures, so that means 3 remains. We'll see how we can hurry up so that we can have time to revise some possible questions along the line. So maybe I'll have to double up by the next class so that I can have at least 1 week to revise past question. When is your exam?
Mid-November. November.
November. Okay, not this October.
Yes.
Are there any set of people that are starting exam this October?
They are level 3 and 4 students.
300 and 400 students?
Yes.
When are they starting theirs?
I think it's October.
Ending?
Yes, ending October.
Okay, that's okay. So today we'll try to look at properties of solid. We'll try to know different ways of classifying solid. What are the different types of solid we can have? You understand the different concept of semiconductor, associated type, and properties. Understand what is the surface tension and factors that affects surface tension. You should be able to understand various properties of liquid and to differentiate between different types of liquid. So that means we will know different types of liquid. What are the different properties for each of them? And can we really differentiate between them? And we'll look at solid. We'll try to see which solid is amorphous. What do we mean by amorphous solid? What do we mean by crystal? So we are gonna look at those things, and we're gonna look at we're gonna look at also different ways of classifying solids, and we shall look at the way for semiconductors. We will know which one is N-type semiconductor and which one is P-type semiconductor. So we'll know the difference between semiconductor and conductor, and also with the insulator. So that is what we are going to look at. Let's start, and you're welcome to this fifth lecture. So types of solid. Based on the regularity of the repeated unit, solid can be classified into amorphous. Amorphous do not have a regular repetition of the unit. You know, like you have draft, or let's say draft, something like draft, or design in your cloth. A certain design will come and then repeat itself all over the cloth matter. So that repeated unit is what we call a unit cell. So based on the way they are arranged, if they are arranged regularly, that's after this one, maybe you look for a tiles. After these tiles, you put the next one, and they go hand in hand. That's regular arrangement form what you call crystal. But if they are not regularly arranged, it is called amorphous solid. But if they are regularly arranged, then it is called crystal. So crystal have regular arrangement of unit cells. Each of those units that forms the bulk of it is what you call a unit cell. Then when you bring them together, after this one, you see this one, you see this one, they are regularly arranged. That is called a crystal. But in amorphous solid, they are not regularly arranged. The unit cell are not regularly arranged. So irregular arrangement of a unit cell gives amorphous solid. But when the unit cells are regularly arranged, we have a crystal. So we can classify solid into crystals and then amorphous amorphous solid, crystal solid. So these are the first level of classification. So crystal solid are those solids that are formed due to regular repetition of identical building block. That building block is what we call unit cell and are called crystal. For example, sodium chloride. So amorphous do not show regular shape because they do not have regular internal arrangement of the unit cell. There's no regular internal arrangement of the unit cell. So internal arrangement of the unit cell. So amorphous solid means a solid without regular form. Glass and polythene are common example of amorphous substances. Glass and polythene are common example of amorphous solid. Those are the common example of amorphous solid. So that is amorphous solid, as we just said, and we say that is amorphous solid. So now, amorphous solid means a solid without regular form. Glass and polythene are examples of amorphous solid. Crystalline solid compared to amorphous have definite heat of fusion, definite crystal lattice, and then definite melting point. So that is it. Can you really differentiate between amorphous and crystal solid? So what is the difference? The difference is that one has a regular arrangement of unit cell, and that is crystal. And the amorphous solid have irregular arrangement of unit cell. They don't have regular form. And the example is glass and polythene, but crystal have a regular form, and actually is formed by, it has a definite heat of fusion, values for heat of fusion, crystal lattice, and definite melting point. That means the melting point of crystalline is a definite, maybe 200. If it's 500, it's 500, not between 500 and 300 and 600. But amorphous, it will be a range. You can't say this is exactly the melting point of amorphous compound. So that is what you see there. So now move on to other classification. We can have macromolecular solid, macromolecule, such as protein. They are large, they have large molecular mass. And discrete molecular solid, we have metals, we have ionic solid. Discrete molecular, we have metals, and we have ionic solid. Crystallography, the study of crystals, so is what we call crystallography. So lattice is defined as the arrangement of geometric points in a definite pattern in shape. Arrangement of geometric points in a definite pattern in space. So how they arrange, how the units, it can be unit cell, the geometric point can be unit cell arranged in a regular pattern in space. That is what we call lattice. So it can also be defined as a regular periodic arrangement of points in space. It can be a point arranged in space. Regular. Look at that word, regular arrangement. So that means lattice will appear to crystal. That's why we say crystal lattice. It's not applicable to amorphous. So when atoms are attached regularly to each lattice point, it forms a crystal. You can see the meaning there. However, instead of an atom, we can have a group of atoms attached to each lattice point. So we can have that. The group is called a basis. So the group, that's our group of atoms attached to a lattice point, is called a basis. The basis consists of the atom, their spacing, and internal bond angle. The basis consists of the atom, their spacing, and internal bond angle. So it talks about the atom, the bond length, and the bond angle. Every basis is identical in composition, arrangement, and orientation. Question: what are characteristics of basis? They are identical in composition and arrangement and orientation. That is one thing. The basis consists of atoms, their spacing, and internal bond angle. So atoms, the bond length, and to the what you call the. So you can look at it and see the what it dash is in a definite part. You can see the answer there is define a regular point in space. So when atoms are attached point, it forms a what? A base atom attached to a regular. So you can, when atoms are attached to regularly to each lattice point, it forms a what? So still find the answer for yourself. One of the following is not a component of a basis: atom, spacing of atom, internal bond angle. None of the above. So of course, you know none of the above is the answer. So none of the above is the answer. So now look at the lattice. You can see a point. This one regular. You can see the point is regular. So that forms a lattice. B, the point is also regular. That forms a lattice. C, the point is also regular and it also forms a lattice. So we can say A is a lattice in 2 dimensions. B is basis. B is basis with 2 atoms. That's 2 atoms only. That's a basis. 2 atoms only for B. Then C is crystal structure, showing the basis of 2 atoms in relation to lattice point. So that is what you see there. That's the difference. Unit cell. What is unit cell? We have already defined that a crystal has a regular arrangement of unit cells. And we also say that amorphous has irregular repetition of unit cells. So, but what is unit cell? That unit that can be used to combine. When they combine together, they form a crystal. So, a unit cell is the fundamental or unit in a crystal. The repetitive arrangement of unit cell in 3-dimensional produces a crystal. Hello? Hello?
Good
Hello?
evening, sir. Good evening,
Okay,
sir.
are you hearing me?
Yes, sir. The network is very bad, but I
Okay,
can hear
yeah.
you.
Okay, so the unit cell is the fundamental unit in a crystal. The repetitive arrangement of unit cell in 3 dimension produces a crystal, just as a wall is built from identical bricks. So if you have blocks and you bring the block, after this one, you put this one, after this one, you put this one, and keep on building, that forms a wall. So now if you bring the unit cell and arrange them the same point, after maybe 1 meter you put, after 1 meter you put, and so on. And by the time you know, that forms what you call crystal. So that unit cell is like a block. A building block for crystal. So unit cell is the smallest unit which produces a crystal when translationally displaced. Is the smallest unit which produces a crystal when translationally displaced. So that is what you call a unit cell. A unit cell represents the crystal may be quite different in size and shape from another unit cell. So what differentiates between unit cell in a crystal system, size and shape? What are the things that differentiate them? What is the smallest component that produces a crystal? And the answer is unit cell. So what differentiates between unit cell in a crystal system? So it is the size and shape that differentiate between one unit cell and the other one. So that is the answer there. So now let's look at this based on the relationship among the axis, angle, and the edge length. There are 7 classes of crystal. There's what you call Bravy's classification of crystal. If you look at crystal, you can talk about length, you can talk about the angle, you can talk about 3 different angles. Now, when you look at, take one of the cube, you have a cube, one side, the other side, and the other side. We used to say X, Y, Z direction. So like if you look at that direction, in a 3-dimensional system, you have 3 angles and you have 3 lengths. So that's one of the length is A, the other length is B, and the other length is C. That's for a typical crystal. You have 3 different lengths. And then out of these 3 different lengths, there will be 3 different angles. One is normally called alpha, one is called beta, and the other one is gamma. So that is a three different ones. So based on what is the size of the length, how is the length related to the other length, are all the sides of the length equal, or are two sides of the length equal, are all the angles equal, or is two sides of the two angles equal? Based on that, we can have different crystals, and the different crystal, that classification is called Brevet's classification of crystal. There are 7 crystal systems based on the Brevet's classification. The first one is cubic crystal. If you look at a cube, all the sides of a cube are equal. That means A, B, C are equal. And all the angles in a cube is also equal, and that is equal to 90 degrees. If you look at your sugar cube, that is 90 degrees. And that example is sodium chloride, and another example is cesium chloride. So a cubic crystal has all the sides equal, and all the angles are also equal. So we move out from the example is sodium chloride that we said. We shall see later that there are 3 different types of cubic crystal. We have the primitive cubic crystal, and we have face center cubic crystal, and we have a body center cubic crystals. But this fundamentally you should know, for a cubic crystal, all the sides are equal, and the 3 basic angles are also equal. Then the next one is the tetragonal crystal. In the tetragonal crystal, you can see A is equal to B, but it's not equal to C. That means 2 sides are equal, but one side differs from each of the other 2 sides. And the next thing about the angle for tetragonal crystal is that all the angles are equal. The example is the white tin and then titanium oxide. The white tin and then titanium oxide are example. They are example of tetragonal crystal. And we have the third one is orthorhombic crystal. All the sides are not equal. None of the sides is equal to each other. That means the A is not equal to B and is not equal to C. But unfortunately, all the angles are equal. So fortunately, all the angles are equal. And example is cadmium sulfate and then mercury bromide. So you can look at the first 3 we have mentioned. In the first one, we have a cubic crystal. All the sides are equal, and all the angles are equal. We stated example there, and the example we stated there was sodium chloride, and then we have another example, and that is we have cesium chloride. So we have the tetragonal crystal. The 3 angles, 2 angles are equal. Oh, sorry, 3 angles are equal, but 2 sides are equal. One side is not equal to the other one. That's the tetragonal. And we have the orthorhombic. The orthorhombic is that all the sides are not equal, but all the angles are equal. So based on all angles equal to each other, and that is 90 degrees, we have the cubic crystal, the tetragonal, and the orthorhombic crystal. So now let's move to another side where all the sides may be equal. We have the next one is a rhombohedral crystal. We have the rhombohedral crystal. So we have the rhombohedral crystal, and in the rhombohedral crystal, all the sides are equal, but only 2 of the angles are equal. And all the angles are equal, but they are not equal to 90 degrees, unlike cubic crystal. So the rhombohedral has some similarity with the cubic crystal because all the sides are equal, but and all the angles are equal. But the difference is that in cubic crystal, all the angles are equal to 90 degrees Celsius. But in rhombohedral, all the angles are not equal. None of them is equal to 90 degrees Celsius. Example is calcium carbonate crystal. And we have the next one, the hexagonal crystal. Only 2 sides are equal. And it has 2 angles, alpha and beta, equal to 90 degrees. So alpha and beta, 2 angles is equal to 90 degrees. Now, and we move to monoclinic. A monoclinic that none of the sides are equal, where the two angles are equal to 90 degrees. And we have the triclinic, none of the sides are equal, but none of the angle is equal to 90 degrees. What's the difference between monoclinic and triclinic? The difference is that none of, in the first one, the angle is equal to 90, but none, in the second one, triclinic, none of the angle is equal to 90 degrees Celsius. So you look at it and you see the rhombohedra, all the sides are equal, and the two angles are, the three angles are also equal, but not equal to 90 degrees. So you should be able to see the differences in the seven classification of crystal, starting from the cubic crystal, and next to tetragonal, and next to orthorhombic crystal, next to rhombohedral crystal, and followed by hexagonal crystal, after rhombohedral crystal, and then followed by monoclinic and triclinic crystal. So these are the different types of crystal system. And this classification based for the seven classifying crystal into 7 groups is called Bravest classification system. So now, in which of the following pairs of crystal system are the angles not equal to 90 degrees? So you can see for hexagonal and cubic crystal, you see for rhombohedral and triclinic. So you can have what is the answer? Rhombohedral and triclinic will be. So now let's see what rhombohedral and triclinic offers. Rhombohedral and triclinic, all the sides, okay, the angles are equal.
Yes. The angles are
No,
not
rhombohedral
90 degrees.
and triclinic, the angles are not equal to 90.
degrees.
So it's just technical way of answering. In which of the following crystal pair are all the angles equal to each other? Cubic crystal and rhombohedral, triclinic and monoclinic, cubic and hexagonal. So what's the answer?
Is it cubic and hexagonal? I know cubic for sure. I'm not sure about hexagonal.
So you can check yourself.
Yeah, that's it. It's cubic.
so that you can check yourself. So in which of the following pair are all the angles equal to each other? So that is
okay.
check the question well. All the angles are equal to each other. So check
all the angles
are equal to each other. Have you seen it there? Have you seen cubic? So it is
tetragonal. There is also orthorhombic, and there is hexagonal.
So it's just for you to know. The difference in rhombohedral is that the angle is not equal to 60. But in hexagonal, the angles are equal to 90. So now let's proceed. Yes,
so if
go on.
Question comes out, will orthorhombic be, is it no, will with rhombohedral be correct, even though it's not equal to 90 degrees?
Yeah, all these angles are equal because you can see alpha is equal to beta is equal to gamma.
All right.
Although it's not equal to 90, but they are equal.
Okay.
Okay, so previous classification of crystal does not consider one of the following factors: angle, side, bond strength. Bond strength is a correct answer there. Cadmium sulfate, hydrogen bromide are example of what? So what crystal is it? The example of that, what crystal?
Orthorhombic. Did I get it?
Check it out. Check it out.
Yes, I got it.
Yeah, you got it. All right. So question continue. A crystal in which all the sides are equal and the angles are equal is called a cube.
Cubic.
A cube in which none of the a crystal in which none of the angles are equal and none of the sides are equal is called what?
What was the last one?
Is it not triclinic?
Yes, that was I was trying to remember the last one.
Okay. A crystal in which all the angles are equal, none of the sides are equal, and all the angles are equal, and none of the sides are equal. It's called what?
We just talked about this one. Oh, I know it's not orthorhombic. I'm not sure again.
And not tetra. Is it not tetra? Is it tetrahedral? All the angles are equal, and none of the sides are equal. Let me take it to your table. You can find the answer for yourself. All the sides are. Are you seeing it?
Okay. None of the sides are equal.
Is it not orthorhombic?
Hello, sir.
Yes, sir.
Good evening, sir.
Yeah, good evening. How are you?
I'm fine, sir.
Okay.
Please, sir, I'm not following you.
Okay. You mean you didn't follow me in this lecture or previous one?
The tetra and the rhombic. So I would like if you can draw the diagram so that I'll be able to identify.
The diagram is let me take you to a demonstration. Okay, let me see if I can bring you the diagram. Don't worry. We can have that. It's possible to have that. Let me come in. Just a minute, I'm coming. Just a minute, I'm coming. Just trying to bring up the diagram. Can you see this diagram?
Yes, sir.
Yeah, so you can see triclinic. So when you compare that diagram, you can compare side by side to see. For cubic crystal, A and B are equal. So that's what we mean by A. When you see A, that means all of them are equal. You understand that?
Yes,
Yes,
sir.
sir.
When you have tetragonal, you have A, but you have C. That means A and B, A are equal. Two sides are equal. One side is not equal, right? When you have triclinic, you have ABC. That means the three sides differs from each other. And this is the angle here. So when we have monoclinic, we have ABC. That means the three sides differ. When you have orthorhombic, you have that. So that means the three sides differ. That is what some of the sketch you can have for it. And you look at the hexagonal, two sides are equal, and the other side is not equal. So that is the side. The angle here, we can have angle here. We can have angle here, then one at the base. So three different angles. One at the bottom here, the bottom of this one, joining the bottom of this one. One at the last one, joining the up here, then the other one joining. Those are the three angles that matters. I think that can give you some explanation about that. So is there do you understand it a little bit more than what you needed?
Yes, sir.
Okay. So we move on. We're just creating some questions based on this. So we move on. So one of the following is an example of rhombohedral crystal. Some of the examples I will post them as PowerPoint later on. So now let's move to amorphous crystals. There are crystals with no identifiable characteristic shape. Amorphous crystal has been found in different urine samples. For example, we have urate. Urate is found in urine and it's amorphous crystal. So at an acidic pH less than 6, an amorphous urate crystal. At a pH greater than 7, they are amorphous phosphate crystal. Then this is a cubic crystal. It has 6 phases. You can count your sugar, for instance. How many phases does it have? 1, 2, 1 up, 1 down, 1 this side, 1 this side. That's 4. 1 this side, 1 this side, 6 sides. Do you know that the cube has 6 faces?
Yes, sir.
Yes. So a cubic crystal has 6 faces. So now there are 3 types of cubic crystal. This is the primitive cubic crystal. All the angles, all the unit in the primitive cubic crystal, all the unit cells are found at the edge of the cube. How many edges does a cube has? 8 edges. 1, 2, 3, 4 up. 1, 2, 3, 4 down. So it has how many edges? 8 edges. Now, these are the angles we were talking about. You can see the angle here, see angle beta, see the angle gamma. So that's how we are talking about the angle there. Now, this is a primitive cubic crystal. The unit cells are at the edge of the cube. Now, the body center is that there will be 1 in the body. When you have a 1 unit cell in the body, you draw a line to all the 4 8 sides. And that is what we call body-centered cubic crystal. There's a unit cell in the body, and if you draw a line to each of the cells, it separates them from equal, and that means the distance from here to here is the same, from here to here is the same, from here to here is the same, and so on. So this is a body-center unit. That's the body-center unit crystal. So we have the last one, face center unit crystal. Face center unit crystal. If you draw a diagonal in each side, the diagonal means from 1 up to down, 1 up to down. At the center of each face, there will be 1 unit cell. So that system is now called face center unit cell. That one is called face center unit cell. So there are 3 types of unit cells now. We have the primitive unit cell, we have the body center, and we have the face center unit cell. The body center and the face center unit cell. So let's move on still. A cubic crystal, each corner occupy an atom or ion or molecule. They do not touch along diagonally. The edges are all of equal length. So we have A is equal to B is equal to C. The angle are alpha, beta, gamma equal to 90 degrees in each face. Each face has 4 corners. By joining the corner of each of a face diagonally, 2 face diagonals are obtained. The center, the 2 faces diagonally meet, is called face center. So now, by joining any 2 corners which are not in the same face, a body diagonal is obtained. There are 4 body diagonal in a cube. All the body diagonal meet at the point called body center. Such arrangement is called body center arrangement. So now we just explained that, and what I'm saying now is what we just explained. You have the edge of the cube here. If you join this point, for instance, to the next point, that is a diagonal. And you join this other one again, that's a diagonal. And if you join this other one again, join this one, you have a diagonal. If that center, the point in which all the diagonal meet is called body center. So this is a body center. This point is body center. So that is why we now call it body center cubic crystal. Now, this is a phase. In each phase, if you draw one line here, join another diagonal, they meet again. This point is called phase center, and that is why we call such crystal phase centered cubic crystal. So we can identify 3 types of cubic crystal. Now let's see something. Let's take a very simple question. Let's take a simple question. How many atoms has the following cubic crystal? One, primitive. A primitive has how many atoms? Now, how many atoms has the following crystal? Primitive. Now let's see. Let's count together. This is the primitive. How many atoms are there? 1, 2, 3, 4, 5, 6, 7, 8. How many are there? 8. So for the body center, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9. Body center, how many? 9. And what of the phase center? Can somebody count it and tell me how many atoms they have? How many atoms do they have?
14, sir.
14.
14.
Yes.
Let's see. How many phases does a cube has? How many faces?
6.
A cube has how many faces?
You see, sir.
The number of faces. Count it here. 1 up here, 1 up here. That's 2. 1 up here, 1 up here. That's what? 4. Is how many? 6. 6 what?
6 faces.
Is it correct?
Yes.
Check for yourself. I want you to understand. A cube has 6 faces. You can compare. I want you to understand why it is 6. If you carry a cube of sugar, count the number of faces, count the up one. When you count the up one, 1, 2, 3, 4, 5, 6. So you have 6 faces. So 6 plus 8 is how many? 14. So just like you said, so a primitive crystal will have 8 atoms. You have 8 atoms. A primitive crystal will have 8 atoms, not 6. And then body center will have 7. Body center will have 9. That will have 9. Because 1 plus the 1 at the center, that is 9. Then phase center will have
14.
How many did he say? 14, yeah. 14. 14. All right. So question, all diagonals from different faces of a cubic crystal meet at A, H center B, face center C, body center D, diagonal center. What's the answer? Face center. The center in which two faces diagonal of a cube meets is called an H center, face center, body center. It will certainly be body center. The number of face diagonal obtained by joining the corners of a face of a cubic crystal is how many? If you know the number of face, each face will have 2 diagonal, 1 up to the other side, 1 up to the other side. So how many faces has a cube?
6.
6. So you have, that answer should be what? 12. Yes. The number of face diagonal obtained by joining the corners of a face, each of them has 2. So the answer here is 2 because we are talking of a single face, not all the faces. So each of them will have 2 diagonal. One side of a cubic crystal is determined as 5 nanometer. Calculate the sum of the length of the other 2 sides. If it is a cubic crystal, all the sides are what? Equal. So there are 3 sides of a cubic crystal. One side is 5. So that means the other side are also 5, 5. So the sum of the length of the other 2 is what? 5 plus 5, which is what? 10 nanometer. So now, question, how many atoms or single can be accumulated in each of the edges of a cubic crystal? How many atoms? 8. If you look at it, each of the edge can carry 8 atoms. How many faces has a cubic unit crystal? 6. We've said that. How many diagonal can each face in a cubic crystal produce? 2. How many diagonal can each body in a cubic crystal produce? You can now see that it can produce what? You can imagine for yourself what it can produce. The body center, let me take you there so that you can calculate it and see. 1 goes from here to here, that's 1. Another 1 goes from here to here, that's 2. Another 1 goes from here to here, that's 3. Another 1 goes from here to here, that is 4. So you can produce, when you have for each edge, 1, you come for this 2, 3, 4. So there is 4 that can pass through the center. So that there are 4 diagonal that can pass through the center. So a crystal in which the atom is spread in each face of a cube unit is called phase center. That is a phase center cubic crystal, FCC. Hexagonal close packing is another form of crystal, but not for cube. Body center cubic packing. A crystal in which atom is distributed in body of a cube unit cell is called body center cubic packing. How many atoms do you expect each unit cell in a phase center cubic crystal to have? In a phase center, we have already mentioned how many should be there. If it's in a phase center, we say 14. How many atoms do you expect each unit cell in a body center to occupy? We say that is 9. Crystallography. Crystal planes are represented by certain number called Miller indices. Miller indices are generally represented as HKL. So crystal can also be classified into, it can be classified into body center cubic structure. It can be classified into ionic crystal. And we have another one called covalent crystal. We have molecular crystal. So we have crystal system can be studied using what? X-ray diffractometer. Diffractometer is what we can use to study crystal. That's what we call X-ray diffraction. So question, one of the following is commonly used to represent crystal plane, and the correct answer there is the Miller indices. Miller indices can be represented with the following letters. HL is either HKL is a real right answer there. HKL. So not A. Now C. Okay. HKL is what we normally use. HKL. HK and L. So that's what we use. Sodium chloride is an example of dash crystal. Cesium chloride is an example of that. Both are example of cubic crystal. One of the following is not a class of crystal. A, ionic, covalent, molecular, metallic. Is molecular is not a crystal. Others are crystal. A crystal structure of a system can be studied using one of the following. We say X-ray diffractometry is actually used. The basic equation for crystal analyzing instrument is the Bragg equation. So Bragg equation is used for analyzing the plane of crystal. So covalent and molecular crystals. In covalent crystal, covalent bonds join all the atoms in the crystal. The structure of a covalent crystal is related to 1, the number of valence electron. 2, the nature of orbital involved in bond formation. 3, the orientation. Example is in diamond. In molecular crystal, the molecules are held together by van der Waals interaction. This crystal acquire the structure which has a minimum energy maintaining the original shape of the discrete molecules. Iodine and carbon 4 oxide crystals are example of this type of crystal. That is molecular crystal. So let's still proceed and see how we can. So common metallic structures. Most of the metals crystal in one of the four basic structures: simple cubic, body center cubic, hexagonal close packing, and face center cubic. So these are the four types of metal crystal structure. We can have a simple cubic for most of the metals, body centered cubic, hexagonal close pack. Simple cubic structure is not very common except for polonium metal, which is packed in this structure. So the simple cubic structure is not very common for metals, but it's found in polonium metal. Alkaline metal also have a simple cubic crystal. Barium also have that. Vanadium also have that. Chromium has that. Molybdenum has that, and some few other ones. Crystal in actually have there are another set of crystal is crystallized in alkaline metal, barium and vanadium, chromium and molybdenum. They crystallize in body center cubic structure, but the simple cubic structure is common for polonium metal. So barium, vanadium, chromium, and few others is body center cubic crystal. So semiconductors is what we now go now. Semiconductors is there are substances that can behave both as conductor or as insulator. What makes them so is that at higher temperature, they will release electron and they behave as conductor. At lower temperature, electron movement is impeded. That means they behave as insulator. So semiconductors are solid which are insulator under normal condition, but becomes a conductor when heated or doped with impurity. So now, two ways. How can you make a semiconductor to become a conductor? You either dope it with impurity or you raise the temperature. And so, and the presence of impurity that is a dopant, is an impurity in this case. So the electrical conductivity of a semiconductor increases with temperature. The semiconductor can be broadly classified into two types. We have the intrinsic semiconductors and we have the extrinsic semiconductors. So this classification is based on which one is donating electron and which one is accepting electron. This is we have intrinsic and extrinsic. We shall see this later. So state two factors that affect the electrical conductivity of a semiconductor. The two things that can make a semiconductor to conduct is the presence of impurities called dopant, and then the other one is that increase in temperature. State the two basic classes of semiconductor. We have the N-type and we have the intrinsic and extrinsic semiconductor. One is called N-type and the other one is called P-type. Types of semiconductor. An intrinsic semiconductor, also called an undoped semiconductor, or I-type semiconductor, is a pure semiconductor without any significant dopant species present. That is a pure semiconductor, no dopant present. It's called intrinsic semiconductor. The number of charge carrier is thereby determined by the properties of the material itself instead of the amount of impurities. So, but when the impurities is what determines the conductivity, that what makes the semiconductor to conduct, we say it is extrinsic semiconductor. So semiconductors with impurities are called extrinsic semiconductors. And semiconductor, they can be classified into N-type and P-type semiconductor. A semiconductor with dopant is called what? That is extrinsic semiconductor. A semiconductor without impurities are called what? Intrinsic semiconductor. The two types of extrinsic semiconductors are what? N-type and P-type semiconductor. N-type means that it's rich with electron, and the other one is that it's depleted of electrons. So N-type, when a semiconductor is doped with an impurities having more valence electron, the impurities that you are now adding to the semiconductor has more valence electron than those in the semiconductor. A N-type semiconductor is produced. Such an impurity can donate an electron to the valence band of the semiconductor and is called a donor. Such impurities can donate electron and is called a donor. So phosphorus, arsenic, and antimony is an example of N-type substances that can be used to dope germanium or silicon. So when such are doped, they can now form N-type semiconductor. So how many valence electrons are present in one? Phosphorus, 2, antimony, and 3, silicon. Give 3 examples of impurities that can act as donor in an N-type semiconductor. We mentioned that in this just now. So we have the p-type. When this impurity is used for doping has less valence electron than the semiconductor, the impurities can accept electron from the valence band of the semiconductor. Such an impurity is called acceptor. So the addition of boron, aluminum, gallium, or indium having 3 valence electrons to silicon or germanium, that's having 4 valence electrons is an example. So the semiconductor has more electrons than the dopant. So that is called p-type semiconductor. So we're able to see that, and we still move further to surface tension. A liquid has a strong intermolecular forces. So you can see molecule in the bulk of a liquid experience these attractive forces in all directions. For instance, if you are in the water, you carry a big heavy or stone. You can carry a very large stone inside the water because that attraction is not too much. There's no serious force inside the water, in the body of the water. But once you want to bring it to the surface, you find out there's so much attraction, and that attraction is actually caused by surface tension because the molecules, the attraction is by sideward and sideward, but inside the body, there is a balance of attraction in all directions. So the situation where the surface of a liquid behaves as if it's covered by elastic skin is called surface tension. If you put a needle on water, crease a needle, it can float on water. But if it floats on water, that means because the surface of the water is behaving as if it's a skin, it also behaves as something that can make something to fall in. That is surface tension. An example is demonstrated by a needle. When you crease a needle, it can float. But if you add something like detergent, it will now sink because the detergent lower the surface tension. So there are substances that can lower the surface tension, such as the detergent. So you see, this is the body of the liquid. The arrow shows attraction is everywhere, but in the surface of the liquid is in one side. That is why the surface, now all the pool is inward and sideward. So that means there's no pull out of the water. So that is the surface tension. It makes it behave as if it's covered by elastic skin. So factors that affect surface tension are molecule having strong hydrogen bond, and metallic bonding also lead to high surface tension. The dispersion force are quite significant in molecules with large atoms and are often more important than dipole forces. So surface tension can be affected by some of these factors we have listed. We have some questions here which you will try for yourself. We will have enough questions so that at least by the end of the exam, you should be able to have some good ideas on how to answer questions. So intermolecular forces is responsible for capillary rise. That's what we call cohesive and adhesion forces. If you put water in a glass, you will see that the water will sink down. There will be what we call lower meniscus. But if you put mercury, you see that it will swell up. It will swell up. So the concave shape of a meniscus of water, concave shape in a glass tube, indicate that adhesive force of water towards a glass are stronger than the cohesive forces. A metallic liquid such as mercury show a lower level in a capillary tube and a convex meniscus because the cohesive forces between the molecules of mercury is higher than the adhesive forces between mercury and the glass. So cohesive forces is force of attraction between molecule, the same molecule, while cohesive adhesive is forces of attraction between one molecule and the other. So for water and glass, water has a stronger force for glass and the water molecule itself. So that is the difference there. So what do you expect? See, this is a meniscus. This meniscus is polar liquid such as water. For A, you see that it has a lower one, but mercury, it has a convex one. You see how the thing rises here, mercury is here. So the cohesive force of mercury for itself is higher than the adhesive force. But for water, the water is at the the force between water and glass is stronger. So that's why you see the depression here. So that is how it is there. So the questions you can try yourself. My time is actually over, so I'm trying to touch everything. So what is viscosity? And it's another property of a liquid that has to do with intermolecular force. And it's a measure of the resistance to flow. That means, for instance, if you if you put water on the table, it can flow. But the same way, oil will not flow the same way. So we say that oil is more viscous than water. The molecule with higher molecular mass will have higher viscosity than the other molecules. So different liquids exist, and we have like kerosene, milk, mercury, water. Mercury is the only metal that can be found in the liquid state. So there are different substances. Some contain a mixture of solid and liquid substances. Some are organic and some inorganic. One of them is mercury, metallic liquid. Some are compound, while some are elements. So some compounds, liquid differs. Some of the liquids are mixture, and some are actual organic and some inorganic. Some are metallic liquid, and some are compound, while some are elements. So that is what we see. So viscosity of liquid, hydrogen bonding. Liquid with large intermolecular force flow slowly. That's what I said there. Then hydrogen bonding could account for the high viscosity because it can bind neighboring molecules together much stronger. For example, water has high viscosity than benzene and chloroform, which have no hydrogen bonding. Glycerol has very high viscosity because of numerous bonds it can form. So that is it. Viscosity, molecular arrangement also has effect on viscosity. Molecular arrangement also could cause high viscosity. For example, heavy hydrocarbon oil and grease are not hydrogen, doesn't have a hydrogen bond, but are highly viscous. So it is the molecular arrangement that makes them viscous. Their viscosity can partly be affected by London forces because molecular and the long chain like molecule may become entangled with each other, like cooked noodles. So viscosity also increase with increase in molecular mass. So you can see what are the factors that affect viscosity. This is the molecular entanglement. It can make it to be more viscous than when they are spaced aside. So we shall continue with this lecture in the next class. If there's any question shortly, you can throw it before I start down, since I have another class. Any question? Any question?
Hello, sir.
Yeah, any question?
Concerning the metallic structure and molecular
Entanglement.
No. When we were treating metallic structure in a BCC and a CCC structure during the crystal and amorphous solid, when we were treating that part, I was not really sure of the metallic structure. There's a question you asked, and you said the answer was a molecular structure. I wasn't sure about how you got the answer.
Okay, let me see what the one you mean. I wish I can see it faster. Otherwise, I will allow you to go and do homework and come back to me on next week. Anyway, I just go and do homework. Next week, you remind me.
All right, sir.
All right. Have a nice time.
Thank you, sir. I enjoyed the lecture, sir.